the project coordinator from Barbados. So we're now, are you there, Brian?
Thanks a lot, Mr. Philippe Agostoni. I'm the chairperson for this session, Alternative Energy and Industry. My name is Brian Lee Chandler. I'm the ITC National Coordinator for the Alliance for Action Coconut 2 project in Barbados. I would like to say a special thanks to the donors and partners, especially the European Union, the CARIFORUM Directorate, the Organization of African and Caribbean Pacific States, Caribbean Agricultural Research and Development Institute, CARDI, who is also celebrating its 47th anniversary. Congratulations. Also, to our important regional partners and attendees, good morning and good afternoon to wherever you are. The areas that we are covering today would be, there are two, biomass, fuel and its derivatives, coconut husk and other biomass waste for syngas production, a renewable energy source for chemical synthesis, and energy generation for electricity. This is being presented by Dr. Adeyanju Anthony Ademola. And secondly, Coco Shells in construction potential use in a biodegradable bronze thermal insulation for the construction industry, being presented by Dr. Krishpersad Manohar. Now, a little housekeeping before I go further. If there are any questions by anyone, could you please post them into the chat, but attach the person that you would like to direct it to. That would make it easier for stating or directing where the questions would go. So I'll jump right into it. So I'll give you a little background about Dr. Adeyanju Anthony Ademola. He obtained his PhD in mechanical engineering at the University of the West Indies, St.Augustine campus in 2012 with high commendations. His postgraduate certificate in university teaching and learning in 2018, and his MSc in engineering and BSc in engineering in mechanical engineering in Nigeria. He received the UENGC 2014 Research Award at the most outstanding graduate researcher in the year 2011 to 2012. He has industrial experience at the Nigerian National Petroleum Corporation and NPC, Concorde Airline and Gas Airline in Nigeria. He's a registered engineer, the Council of Regulation and Engineering in Nigeria, COREN, C-O-R-E-N, member of the American Society of Mechanical Engineers, ASME, and a member of Nigerian Society of Engineers, NSC. He's an academic member of Antinir, A-T-I-N-E-R, Greece, and a senior member of the CBEES Hong Kong. His research interests includes solar thermal energy, hydropower, geothermal, biomass, and biogas, heat transfer, refrigeration, air conditioning, gas, and steam turbine. What a lot. It goes on. He has published several research papers in learned journals and presented papers at several international conferences. He's presently lecturing at the Department of Mechanical Engineering, University of the West Indies, St. Augustine campus in Trinidad and Tobago. So without any further ado, I yield the floor to Dr. Adeyanju Anthony Ademola.
Okay, good afternoon. Good afternoon, the chair and everybody. Actually, can I be able to share my screen?
Sure.
Okay. Okay, good afternoon all. And I will be presenting on the comparisons of coconut husk and other biomass waste for syngas production. My name's Anthony Adeyanju. Okay. The presentation contents will follow introduction, methodology, resource and discussion, and the conclusion. Okay, the introduction will be, actually I will be presenting mainly on the biomass waste conversion to energy. Okay, and I'll be looking at biomass waste like coconut husk, bagasse, cocoa pod husk, and also sawdust. Okay, I will be looking at the comparisons of all these biomass waste in generating syngas. Okay, and the transition background now, the transition from natural gas obtained from fossil fuels. Okay, from fossil, let me just take this from here. Okay, so the transition from natural gas obtained from fossil fuels and well exploration to gasification of biomass to obtain syngas, which is cleaner and renewable, is favorable due to its similar usage in power generation, ammonia, and methane production. Okay, and the biomass waste so biomass waste to energy. So we can see that the conversion of biomass waste can be in two methods. That is, we can use biochemical process, and we can also use thermochemical process. The biochemical process is accomplished through the breakdown of organic materials, as we can see in the diagram here, and also the organisms. Okay, and the disadvantages of this process is one, the high cost of catalyst, two, the extensive preconditioning of the feed, then three, the production of a specific production of the product. For example, it's producing ethanol. Then the thermochemical process, which is accomplished by heating the biomass to a temperature between 500 degrees Celsius to 850 degrees Celsius in the presence of air, oxygen, or steam. Okay, in the presence of oxygen, this is a term syngas. In the presence of oxygen, we call it gasification, whereas in the presence of in the absence of oxygen, it is pyrolysis. Okay, let me just take this one. Okay, so we have the syngas production now. Syngas is the resultant gas from biomass gasification, and it consists of carbon monoxide, hydrogen, carbon dioxide, and methane. As you can see from here, that is the biomass is fed into the gasifier, okay, and with the heat supply to heat the bed at rate of 500 degrees Celsius to 850 degrees Celsius, you will produce the syngas. But syngas, we still need to pass through some process like scrubbing the oil, scrubbing the carbon dioxide also. Okay, so the product is carbon monoxide, hydrogen, CO2, and CH4. So the benefits of this syngas is one, cheap cost of waste and the ability to recycle it. It is an incomplete combustion process that produces less carbon dioxide, that is less greenhouse gas is produced. Then we have the reaction that occur in the this gasifier, we have the major reactions that occur are, number one, drying. The most so present in the biomass is converted to steam. Then the second one is pyrolysis. Okay. Then we have the third one, oxidation, where the at temperature of 700 to 400 degrees Celsius, the charcoal reacts with oxygen to produce carbon monoxide and heat. Then we have for reduction, occurs at high temperature where CO2, H2 and CH4 are formed in the resulting gas, and that gas is known as syngas. So the chemical equation is biomass plus O2, which will form carbon monoxide plus H2 plus CO2 plus H2 and the plus CH4. Okay, that is. Then we have the present world syngas market. We have the global market for syngas is dominated by ammonia industry. As you can see in this diagram, the ammonia dominates about 53% of the syngas industry. We have 23% for electric generation. Then we have 11%. Sorry. Then we have the 11% for refineries. Then we have 11%, 23% in refinery, 11% methanol, then 4% electricity generation. Then we have 8% gas to liquids generation. And then we have others. So other important includes generation of hydrogen for use in refineries, processing of hydrogen and methanol power generations. Okay, so these are the present world syngas packets. So the power generation of using the syngas, using biomass gasification is as follows. As you can see, we can from the biomass enter into the gasifier. The gasifier will combust. Then we produce the syngas. We cool the syngas. Then clean the syngas also. Then the syngas can enter into gas-fired boilers to generate heat to district heating building. Then also we can use it to run the gas engine through a generator to produce power to the local grids. So that's the procedure for power generation using biomass gasification. So I want to look at the experience of some countries that have used this biomass gasification system. For example, India, the India Renewable Energy received the 2009 Ashden Award for replacing diesel generator with biomass gasification system. The gasification plant supplies up to 128 kilowatts of electricity to small businesses, farms, and households in Bia through a local grid spanning about 1.5 kilometers. Then the plant cost about US $170,000. Whereas the net percent was spent on gasifier and 10% of it on generator. Okay, then we have the approximately 30% of the plant was subsidized by the government. Then US dollar $0.04 per kilogram is paid to local farmers for supplying biomass. Okay, and the biomass used in that case is the tree stems of a tree known as Adeyanju. That's what they use to generate the syngas. The customer are charged about US $0.15 per kilowatt hour or for the electricity. Okay, so that is for the India experience. Then we have the Germany experience. Okay, driven by the high prices of fossil fuels, about 50 wood gasifiers have been built and installed in Germany between 2000 and 2010. In 2008 alone, at least 25 gasifier plants with outputs ranging from 10 to 270 kilowatts were installed. Okay, so the plant operators experience favorable conditions through the guarantee high energy feed tariffs of about 0.2 euro per kilowatt hour. Then we have the Madagascar experience, where the company called Bioneer installed 4 gasification units in Madagascar. Okay, then the feedstocks used are rice husk and corn stalks. Okay, the gasification unit with rice husk has a power capacity of 40 kilowatts. So the rice husk was collected from the rice mill in the village That is, they collect about 2 tons per day. Okay, so the residue was collected for free at the beginning, and later the farmers decided to sell it to Bioneer company. So the corn stalk also has a power capacity of 30 kilowatts, and the corn stalks are collected for free from the farmers after producing corn around the Port Beggar. So 1.5 kilogram of corn stalk is needed to produce 1 kilowatt of the energy. That's for the Madagascar experience. Then we have the methodology now we use for this particular syngas production. Okay, the sample used are, we have the sawdust, we have the cocoa pod husk and the coconut husk and bagasse. Okay, so actually we are discussing on the coconut husk mainly, but I have to put the, because I made the comparisons between the cocoa pod husk, bagasse, coconut husk, and the sawdust, so as to be able to know the energy generation per samples. Okay, so the cocoa pod husk is a byproduct of the cocoa industry that is produced after the cocoa beans have been removed from the fruit. Okay, the pod husk accounts for 52 to 76% of the weight of the cocoa fruit. Okay, 10 tons of cocoa pod husk are produced for every ton of dry beans produced, which is a major problem because it has a problem for waste management. Then we have also bagasse. It's a dry woppy residue that left behind after sugar cane juice is extracted. So that is bagasse. Then we have coconut husk, which contains cellulose, lignin, pyrogenous acid, gas, charcoal, tar, tannin, and potassium in their chemical characteristics. So coconut husks are mostly used in direct combustion to produce charcoal. Otherwise, they are just discarded. That means it's just discarded. So we can also, it's better. Coconut husk may be turned into high value fuel that can be used in place of wood and other conventional fuels. So coconut husks have a lot of potential for usage in power plants because of the availability and low cost. So that is those are the samples we'll be using for the analysis. Then we have the samples. The figures here show the samples like this. We have the sawdust, we have the cocoa pod husk, then coconut husk, then we have the bagasse. Okay, so all these are grinded, after well dried, and blended to a grain size of like 3 to 5 millimeter. Okay, before we started inserting them inside the gasifier. Okay, so the proximate and ultimate analysis of the samples were performed also. The approximate analysis were performed to determine the moisture content, the ash content, volatile matter content, and fixed to carbon content for the samples, sawdust, coconut husk, cocoa pod husk, and bagasse. Okay, then we also carry out the ultimate analysis to know the caloric value and the carbon, hydrogen, oxygen, nitrogen, sulfur content composition in sawdust, in coconut husk, in cocoa pod husk, and bagasse. So we also carry out that. So this is the diagram we are seeing here, the pictures we are seeing here. They are the prototype of the full batch gasifier. This is the fabrication process that was taking place in the workshop at UWI. Okay, then we have the experimental setup. You can see from the right hand here, this is the gasifier. That's the gasifier here. Then we have the setup for the experiment. Each sample, the sawdust, cocoa pod husk, coconut husk, and bagasse was dried and bleached to 3 to 5 millimeter. Then the feedstock was fed into the reactor at a rate of 0.4 grams per second. So once the reactor reached the temperature of 450 and the fluorescent agent had a flow rate of 9 liters per minute, then you can feed into the samples. Okay, each step was repeated using a silicon dioxide and nickel catalyst. Okay, the catalyst was used also to be able to know the effect of catalyst on those samples. in producing of the syngas. So the reason we're using a gas analyzer, and we're taking a 7-minute interval. So the procedures were repeated for all the samples. Okay, so those are the experimental setup. Then we have the properties of syngas produced from gasification of samples without catalyst. So the samples without catalyst, the properties, efficiency, carbon monoxide, nitrogen oxide in ppm, HC, hydrocarbon produced, then carbon dioxide produced, then the air fuel ratio were taken for sawdust, for cocoa pod dust, for bagasse, and for coconut husk. Okay, so we look at that for when there's no catalyst. Then the second one was also look at when with catalyst, with nickel and silicon dioxide catalyst. We also look at that one and take the properties for the efficiency of carbon monoxide, nitrogen oxide, hydrocarbon, carbon dioxide, and air fuel ratio for the samples also. Okay, so we can see from here, this is the syngas produced from the samples. Okay, after gasifier, then we have the flame generated from that particular syngas after tested. So this flame is not explosive because it's just around the fuel to air ratio is about 10% to about 13.8%, whereas the lower fuel the flammability limit for gasoline is about 1.4%, and for CNG is about 5%. So for this particular syngas, the range is about between 10% and 13.8%, which is not explosive. Okay, so the next slide is the gas produced. That's the syngas produced from this particular experimentation. That is the syngas produced there. So we now look at the composition of those particular when we take for the catalyst, when we use hydrocarbon generated for each of those particular samples, like for sawdust, cocoa pod husk, bagasse, coconut husk. We can see from this diagram that from this chart that about 7928 ppm was generated by cocoa pod husk, and 3869 ppm was generated by coconut husk. Then we have 3576 ppm generated by sawdust, and 1679 ppm generated by the bagasse. We are comparing this with the sawdust that is in existence before. We can see that the production of coconut husk is even higher than that of sawdust. So that means the coconut husk and the cocoa pod husk and bagasse can also be used for syngas production. Okay, that is for the hydrocarbon, amount of hydrocarbon produced. Then we look at the comparison of the CO content. Okay, for the hydrocarbon produced when you are adding the catalyst. So when we add catalyst reduce the production of hydrocarbon. For example, catalyst reduce the production of coconut husk at 3869 ppm to 1869 ppm. Okay, and that of cocoa pod husk from 7928 ppm to 4702 ppm. Okay, and that of sawdust from 3576 ppm to 961 ppm, and also the bagasse from 169 ppm to 1089 ppm. So that is when you include the biogas, catalyst. So we now look at also the carbon monoxide production produced from these samples. You can see that from the diagram here, we have the highest production of carbon monoxide from coconut husk here. Then it can be reduced when we add catalyst. Catalyst reduces to 8.26%. from 12.62%. That means the effect of catalyst on the syngas production reduce the amount of carbon monoxide produced. Okay, then the same thing applicable to sawdust here from 12.3 to 6.19%. Therefore, also cocoa pod dust from 11.06 to 2.97%. Same thing with bagasse from 7.94 to 6.83%. So the same thing, we look at the amount of carbon dioxide produced. It ranges from 11% to 15.6%. And from the literature, the carbon dioxide produced for syngas is ranged from 5% to over 16%. Okay, so that means the carbon dioxide produced is still within the range of syngas production for carbon dioxide. So we can see that even the effect of catalyst is also felt in the carbon dioxide produced. For example, in coconut husk, we have the 15.6% of carbon dioxide produced. So when catalyst is added, it reduced to 13.6%. The same thing with the bagasse, which produce also 13.8% of carbon dioxide, and the catalyst reduced it to 12.5%. So there's a great effect on that particular of catalyst on the production of this syngas in carbon dioxide composition. Okay, so we have that, and we also have look at the air to fuel ratio of the samples, and the ranges from 10.24 to 13.8%. Okay, and the air to the fuel air ratio for the so we have for the 10.24% with catalyst added to that, I mean, without catalyst, we have 10.24% for cocoa pod husk and 12.52% for when catalyst is added. So the highest here for the air to fuel ratio will be 13.8% for bagasse with catalyst. So and for coconuts, we have 13.75% with catalyst, whereas 13.29% without catalyst of air to fuel ratio was produced. Okay, so from this, we reach a conclusion that the comparison of biomass waste and the effect of catalyst on syngas production were examined in the study. So due to their high volatile matter and cellulose content, as well as low moisture content, the samples, that is the sawdust, coconut husk, cocoa pod husk, and bagasse, were found to be appropriate for use in the generation of syngas. Okay, cocoa pod husk also without catalyst had the greatest hydrocarbon content as 798 ppm, whereas bagasse had the lowest as 1,679 ppm. Sawdust and coconut husk generates 3,576 ppm and 3,869 ppm respectively. Okay, the catalyst prevent the production of tar and other heavy hydrocarbons from the experimentation. Then we have the lower flammability level of syngas is higher compared to that of CNG, where we have the CNG to be 5% and gasoline is 1.4%. So that means gasoline is explosive when you when it dies with in the atmosphere, so it can, that is flowing in the air. But the syngas produced from this study has a lower flammability in the range of 10.24 to 13.8%. Then the HC, the hydrocarbon IS value was determined to have a lower explosive limit of 0.8% from this particular. That means this value was enough to ignite a flame in testing, but it was well beyond range of any possible candidates to be deemed explosive. Okay, that is so, and also the conditions of operating gasification plants are: one, high and constant availability of cheap, appropriate biomass fuel is required. Two, availability of an experienced manufacturer. Then, three, continuous availability of specialized know-how for maintenance and operation that is not to be financed through the operational profit. Low labor cost, and so that is the requirements for a gasification plant. Okay, so that is I think those are the bibliography used for this particular study. So thank you. Thank you. That's it for me.
Thank you, very kind Dr. Adeyanju, Anthony Ademola, for your impressive presentation. A lot was learned there, and it was a mouthful, very impressive. We move over into the next presentation, which focuses on Coco Shells in construction potential use as a biodegradable porous thermal insulation for the construction industry. This is being delivered by Dr. Krishpersad Manohar. He is a senior lecturer in the Department of Mechanical and Manufacturing Engineering, UE St. Augustine. He joined the Faculty of Engineering in 1995, and over the years he has been actively teaching and conducting research in renewable energy, building thermal insulation transfer, and thermal engineering field, including air conditioning and refrigeration. Presently, he is the leader of the Thermal Engineering Group, member of the American Society of Mechanical Engineers, ASME, member of the American Society of Heating, Refrigerating, and Air Conditioning Engineers, ASHRAE, and a foundation member of the ASHRAE CARICOM chapter. We look forward to an interesting presentation. Doctor, the floor is yours.
Good afternoon, everyone. Thank you very much, Chair. All protocols observed. I'd like to share my screen, please.
Sure.
All right. Good afternoon again. So today we are looking at the commercializing of the cocoa waste, and as presenters before said, we should not really be calling it waste. We're going to look at this in the aspect of using it as thermal insulation. So first I'm going to address the concern as to why. Why should we be looking at thermal insulation that is biodegradable? So from this picture here, you are seeing, or you would get a feel of what kind of waste is generated. And a lot of it is from the construction industry. And the problems that are faced when you see we have retrofitting, refurbishing, reconstructing of existing structures. One of the major problems is disposal. So the man-made non-biodegradable materials, such as the polystyrene, polyurethane, polypropylene, fiberglass, etc., that we are accustomed with, they pose a big problem for disposal. In fact, in 2021, publication by the Construction Research Center in Canada, they indicated that despite the advantages of the polymetric products in the construction sector, there are several challenges to their use, and one is the disposal. Another issue with existing thermal insulation, so building thermal insulation, I'm looking at, so insulation that is used in buildings, is the high energy intensive production. These materials use a lot of energy in their production, and that gives it a very high carbon footprint compared to other construction materials such as stone, bricks, concrete, etc. Example, making of fiberglass insulation is an energy intensive process, up to about 10 times more than eco-friendly processes. Another issue is the poor recyclability. These non-biodegradable materials, they have a very, very long time when you put them in the landfills for decay. And also, they lead to health hazards, for they have toxic chemicals in it. For example, the flame retardants that are very toxic. And when these toxic chemicals leak into the landfills, well, you know, they poison the environment, leak into the water courses, etc. So it is a very challenging situation. And presently, there is a drive towards moving to more biodegradable, environmentally friendly alternatives. Now the question, can coconut fiber be used as biodegradable building thermal insulation? So I'm going to examine that in the next couple slides. You see, to be a building thermal insulation, the material must have certain properties and certain characteristics. So we're going to now look at the properties and characteristics of coconut fiber. So the first one is biodegradable. When we say biodegradable, in this sense, what we're looking at, this term biodegradable would refer to a material that occurs naturally, and when disposed, will decompose without causing any adverse effect on the environment. So I'm sure you will agree that coconut fiber would fall and fit this description. So one, it's biodegradable. Another property of building thermal insulation is that it should be fibrous. And so you talk about the fiberglass. So the fibrous material, what it does, it breaks up the air pockets, reducing convective heat transfer and therefore making it an insulator. So that is very brief and superficial. Any further questions I will address. Now, the waste material from the copra of coconut processing industry show a high degree of fibrous content. And one of the speakers before, Mr. Thompson, I think, was saying that he has a large amount of fiber piling up. So high degree of fibrous content. When shredded, the resulting coconut fiber showed physical properties of fiber with mean diameter of 2.67 millimeters. And the range of the fiber diameter was from 0.014 millimeter to 0.052 millimeter, with a standard deviation of 9.04 by 10 to the minus 2 millimeters. And these measurements were done at Kereri way back in 1996. Another aspect that building thermal insulation must satisfy is it should be lightweight. It should not be very heavy. Now, when arranged in a slab-like form as a thermal insulation batt, the minimum density of coconut fiber without settling was around 40 kilograms per meter cube. So this means that we cannot get coconut fiber building thermal insulation less than the 40 kilogram per meter cube if we just use it as the natural fibers as they exist. We can get it lower, but we'll have to use different additives. And later on, we'll see that that would not be wise. But the main thing about thermal insulation is the thermal conductivity. Do coconut fiber satisfy this requirement to be used as a building thermal insulation? So thermal conductivity measurements were conducted in accordance with the ASTM C518 standard. The apparent thermal conductivity, the symbol used for thermal conductivity is lambda, was measured with the laser comp Fox 304 apparatus. These measurements were under steady state, one-dimensional test condition with heat flow upwards. Now, this test equipment is one of the most accurate methods for measuring thermal conductivity. The laser comp 304 used a 305 millimeter square test specimen. And the results here, the test equipment provided that lambda with plus or minus 0.2% repeatability and plus or minus 0.5% reproducibility. And the equipment is designed to measure thermal insulation. So the range at which it operates is between 0.005 watt per meter Kelvin to 0.035 watt per meter Kelvin. So this is specialized equipment for this kind of work. The coconut fiber was tested with 52 millimeter thick, so approximately 2-inch thick insulation batt. And the mean test temperatures were 15.6 degrees C with a delta T of 16.3 and was also tested at 21.8 degrees C mean temperature with a delta T of 13.2 degrees C. So question may arise, why these sort of odd temperatures and not something close to what we have in Trinidad or the Caribbean? Well, you see, our buildings here, as you know, are not really thermally insulated. We don't need it. So the point here is that we're looking at thermal insulation for the countries that experience the cool climate. Now, the test specimens were arranged from the lowest density that it can exist, which is 40 kilograms per meter cube, that is existing naturally without settling, and up to 90 kilograms per meter cube. Tests were conducted, and for each sample, at least 3 tests were done, and the mean test results are shown here on this table. So the average of the 3 tests for the 40 up to 90 kilograms per meter cube density specimens at the mean test temperature for 15.6 degrees C and 21.8 degrees C reflected on this table. Now, those of you who scan in it quickly would see that it dips and then it goes back up. Now, that is very important. One, the thermal conductivity fall within the range of the 0.03 to 0.06 watt per meter Kelvin. This range is normally associated with building thermal insulation. So one tick mark, yes, coconut fiber can be used as building thermal insulation. The other characteristic feature you see here, from the experimental results for the coconut fiber that was shown on the table, the general trend associated with loose fill thermal insulation was shown. That trend is as density increases from the minimum possible value and the density increases upwards, the lambda or the thermal conductivity would decrease to a minimum that is the optimum value, and then increase if you increase density further. So the density range tested, why I stopped at 90, because I achieved the minimum density. And it is the minimum density that would give you the minimum thermal conductivity at that optimum density was achieved. That will give us the minimum thermal conductivity. So that is what you would want for your thermal insulation, the lowest apparent thermal conductivity. So coconut fiber, another tick mark, did fall and satisfy that condition. So the increase of lambda with mean test temperature. So again, from the table, it showed that as the mean test temperature increased, the thermal conductivity, the corresponding thermal conductivity values at the respective densities increased. Now, the question, how does thermal conductivity of coconut fiber insulation batt compare with existing or traditionally used building thermal insulation? So here now, on this graph is a comparison. So we compared like the traditional glass fiber and so on. And you would see that the coconut fiber, and I also tested sugarcane fiber, they show higher apparent thermal conductivity than, like, for example, polystyrene and glass fiber. But bear in mind, this scale is very fine. We're looking at 0.03, 0.04, 0.05, 0.06. So it's very fine. And the minimum thermal conductivity at the optimum density is well within the range used for building thermal insulation. So from this comparison, yes, coconut fiber can be used as a building thermal insulation. Now, how far have we reached into making this a reality? So since we're talking about the coconut, I would like to use the example of a plant. So my question, do we have the seed for this idea to mushroom and blossom and bear fruits? So in this case, I'm looking at the seed as being the scientific research and the data that show coconut fiber has the characteristics and the properties for use as building thermal insulation. And that has been established. So this data is available from research, from the research I did at the UWI. So I think we have the seed. But as you would all know, having a seed and getting fruits is a very big jump. Because after you have the seed, you would need some soil and water. Do we have the soil and water? Well, the availability of the copper in Trinidad and Tobago to generate that raw material can be compared to the soil and water. Do we have the technology to do it? Well, I think Mr. Thompson was referring to some equipment, and we have the technology. So short clip here. Yes. So the technology exists. This is a very small scale machine. You have large scale machines. So there is no need to reinvent the wheel. That technology exists. What else exists? Can we make the extracted fiber, the unprocessed coconut fiber, into insulation bath? And yes, that technology exists. You just have to buy the machinery. So no need to, again, as I said, reinvent the wheel. So we have the seed, we have the soil, we have the water. But that's not all you need for that plant to grow and bear fruits. We need some more things. Of course, you need sunlight. Are there any rays of sunlight for this coconut fiber to be used as building thermal insulation? Well, let's take a look. Here, in this picture, what you're seeing, this is an article that was published in physics.org on the 7th of March, 2019. We see Professor Walker and Dr. Platt here holding up an example of the research that they are doing. This is a collaborative project between the University of Bath and the Brighton University in France, 5 other academic and non-academic partners, funded by the Integre VA France England program. Now, why they are doing this? This research is being pushed because the UK government has set the UK construction industry the aim of halving its greenhouse gas emission, cutting it by half by 2025. So 2025 is just around the corner. So they are busy trying to get alternative, biodegradable building thermal insulation. Now, the idea of using existing materials or co-products could lead to significant reduction in emissions associated with natural resources used in the manufacture of traditional energy-intensive insulations such as glass wool and rock wool. So the question, can we capitalize on these mushrooming markets for natural, biodegradable thermal insulation, such as coconut fiber? So I would like to classify this as some sunshine. So we have some sunshine now. So we have the seed, we have the soil, we have the water, and we're seeing that there is some sunshine. How about the space to grow? and mushroom and bear fruits. So you see, for this initiative to succeed and to get off the research phase from the lab, we need a lot more. And I'm getting the idea from this webinar that there is hope. We'll need funding to develop the final product from this research phase. And Mr. Thompson gave an idea of the cost of that kind of machinery and the cost of funding to go from research to a final commercial product to hold in hand and say, hey, look, this is what we have. Then that still won't give you fruits. We need to do market research, and we need to really market these products in the foreign countries, because thermal insulation in Trinidad will be a no-no. Building thermal insulation, that is. So this is a foreign exchange earner, marketing these products in the foreign countries. So a lot of help is needed, because this is now outside the reach of the engineers at the mechanical department. This is a different expertise, and we would need help in that aspect to get the fruits for the country. So thank you all for joining and giving me this opportunity to make this presentation. Thanks. Back to you, Chair.
Thank you very much, Dr. Krishpersad Manohar. That was a fantastic presentation. It actually piqued my interest at the potential that we can have in the Caribbean, especially with regards to energy efficiency, insulation, all against the whole, well, the recent Paris and COP26 meeting, where it shows that we are going to have extreme weather conditions. This is something that has great potential for not only the Caribbean, but the rest of the world. So with that being said, I open up the question and answer segment so that the viewers can have some sort of interaction with the presenters and encourage some sort of invigorated conversation to yield further explanations and to go deeper into these two areas of concern. The floor is open to everyone at this point in time. Okay, so we have a question for Dr. Adeyanju. Is anyone in Trinidad using this technology? Is it feasible in light of expensive electricity availability from natural gas? That's one question. Dr. Adeyanju.
Oh, thank you. I think is anyone using it in Trinidad right now? I don't think so. And whether it's feasible in light of inexpensive electricity available from fossil fuel, yes. Actually, most of the countries that have been using this gasification system, they don't have natural gas. And like in Trinidad, where we have natural gas, I think it may not be feasible because of the natural gas. Okay, because already the natural gas producing electricity for us in Trinidad is not inexpensive. It's not expensive really. So, and unless if we are looking at the future, we can use the gasification of biomass waste to generate electricity. But in the case of other area like production of ammonia, okay, production of methane, and we can use it in also thermal. Okay, but in the area, most country, if you see that the diagram I showed when I was presenting for the market of syngas, I think we have the 53% cover that of ammonia production. I think that can be feasible in the case of Trinidad, because I think the ammonia company in Trinidad will be able to use the syngas for their for their production, for the production of ammonia. So I think it is feasible in that area, using it for ammonia production.
Thank you for answering that particular question. I think the other question that was asked in relation to that is basically answered. And I would, just for transparency purposes, I would repeat it. Is this research ready for implementation on a large scale by a TNT entrepreneur?
Yes, this can be used by the TNT entrepreneur in a large scale, because the one this prototype we built in the university was able to produce. Prototype we used in testing the biomass waste for the syngas production, was able to produce, and I was able to, that is, as you say, can see in the diagram that the hydrocarbon produced by sawdust, by the coconut husk, and by the other biomass waste were in large quantity. Okay, so that means if we implement in a large scale, that means we can be able to produce at the larger quantity, okay, that can be used by the this ammonia industry. Thank you.
Thanks a lot. I have a question for you.
Yes.
So we're looking at the thermochemical process versus the biochemical process, and
Yes.
Based on the country that you're operating from, I'm talking within the Caribbean context, the different sizes in terms of the economic space. Say you're having a smaller country, would this technology be applicable versus the biochemical process, which probably would be bioreactor, for instance, and this is in light of the feedstock availability.
Yeah. I think the feedstocks are available in most of the Caribbean, like the coconut husk we are talking about is available. Then the bagasse is available. We have even cocoa pod, even sawdust is available everywhere. Sawdust. This is being used in countries like India, in Cambodia, Germany, and so many other countries like that. They have been using it to produce syngas. Okay, so I think the thermochemical conversion is feasible, because that is what we use in our experimentation at UWI. Okay, we build the gasifier. Okay, and we just test. We use those samples to test the gasifier to produce syngas. So if this can be used easily and in large scale, even with the ammonia industry. Thank you.
Thanks a lot. And I have one more last question, and that's a very technical question in terms of the kilowatt hours that this would produce the syngas process. This is the heat process. How do you maintain how would you propose the kilowatt hours be kept low, so it is a very viable option for users of this renewable energy technology?
I think the production, this particular amount of coconut husk, for example, coconut husk, 1.5 kilogram of coconut husk will be able to generate 1 kilowatt of energy. Okay? Yeah.
Thanks a lot.
Okay. Thank you.
Any other questions from the audience? There's another. Okay, Dr. Dr. Adeyanju again. There's one more question. Can this system be used at home on a say at the home level?
I think yes, I think it can be used on a home scale level for us to produce methane. Okay, because syngas is also the constituents of, I mean, the result from syngas, the composition of syngas is of methane, okay, then with carbon dioxide, carbon monoxide, and hydrogen. So if these hydrogen, the carbon monoxide, carbon dioxide are scrubbed, okay, the carbon dioxide, those carbonic oxide can be scrubbed using ethylamine solution. So if we do that scrubbing, then you can live with methane, which can be used for cooking. Okay. That's
very good.
Question. Yeah.
Yeah, this is a very good answer.
Yeah.
Thanks a lot. Any other question? Okay, this one goes to Dr. Manohar. Does breed or variety make a difference in thermal conductivity? Basically, which variety is best all around? So they're basically asking what variety of coconut is best to be used.
Okay, thank you, Chair.
You're welcome.
It is the fiber that makes the thermal insulation effective. It is the fibrous property that breaks up the air pockets and remove the convective heat transfer process. Okay? And that is why when you have the low density, you would have a high thermal conductivity because the pore spaces are big and you have convective heat transfer present. So that's why the apparent thermal conductivity was used, because it's a combination of conduction, convection, and radiation. So at the low density, the air spaces are large, and you also have, so if you hold up a low density insulation, you will be seeing through and through some parts. Therefore, you would also have radiation. As you increase the density, the spaces reduce, convective heat transfer reduced, it gets thicker, radiative heat transfer reduced. And that's why the graph will show a fall. Then it reaches the optimum density that gives the lowest thermal conductivity. As you increase after that, then the conductive part now comes into play. So it is really the fibers and not really the variety of coconut that would matter. Okay.
Thank you. Thank you for that. I have a question that follows on from that particular question. What would this mean for building codes? And then what would be the estimated life cycle of the coconut material?
All right. So for building codes, one, it satisfies the requirement for building thermal insulation. It falls well within the range for building thermal insulation. And as the research from Bath is showing, they're using straw husk from the corn husk and so on that they have available. They don't have coconut. That's why I'm hinting that we should jump on this.
Yeah.
The next thing about the coconut fiber, one, it's moisture resistant. And again, coming back, I keep referring to Mr. Thompson's presentation where he was talking about how long it will last.
Mm-hmm.
It lasts very long. It will last way longer than corn husk. It will be moisture resistant. Another advantage, if your insulation gets wet, you can dry it out and reuse it. And some of the presenters talked about long time. And I remember as a small kid, we had coconut fiber mattress.
Yes.
Your mattress get wet. What do? Did you throw it away?
Throw it out to dry.
You throw it out to dry and you still have your mattress. So the coconut fiber insulation has that advantage. If your fiberglass gets wet, what happens?
Oh, it's a big problem.
You can't do anything but throw it away. So there are many other advantages that I didn't highlight. About the lifetime, it will last very long. Now, another research I did, and I'm just throwing in this. This was conducted since 1986, and I used the bagasse, and I made a ceiling tile. And I have that ceiling tile in my office right now, and it's still there. It didn't fall on my head as yet. So, and Dr. Adeyanju could confirm that. So, the lifetime, it's long. It has advantages over the conventional insulation, and it meets the building code requirements. It is within the range of thermal conductivity for building thermal insulation.
Okay. Any other questions, anyone, for Dr. Manohar? Well, I have a couple more questions, Dr. Manohar.
Sure.
In reference to the work that CrossQ would have been doing with labeling and energy efficiency, and this is a regional project, how do you see this particular product being labeled and recognized as a standard for the Caribbean?
This product is looked at as energy savings because when you insulate your building in the summertime, so now I'm looking at, as you know, in Trinidad, we don't have insulations in our walls.
Yeah.
So if you live, say, in North America, you would insulate your building. That will save you a tremendous amount on your electricity bill for cooling. So it is saving. And of course, all that will go back and tie back. I don't know if I'm getting your question correct, but it will tie back into saving electricity, greenhouse gas emission, blah, blah, blah. You can trace it all back with all the talk that's out there.
It does. It does speak largely to it because it's all about improving energy efficiencies. That one in particular was focused on labeling for the importation of, say, refrigerators and those things are energy efficient to promote then the renewable energy uptake. So I see this largely as something that will contribute to that. But one thing is, which I'm not clear on, would be like, how then would you manage the pest elements? Seeing that we're in the tropics and we have mice, rats, and then mites and those things that can then maybe over time, if they get into the actual wall and at the material, how would you manage that?
Okay, so the ceiling tile that I still have in my office, what I used, well, this one was with sugarcane fiber. So that has sugar in it. Right. And I used cornstarch that you use for cooking as the binder. And I mixed into the cornstarch an insecticide.
Okay.
So it's still there. Without, I removed it about 4 years ago to look at it, and it's still in good condition. So coconut fiber would have now the added advantage of not having any sugar.
Right.
One, coconut fiber is highly, I think it's fungus resistant and so on. So you have some advantages. However, to address the concern directly, you will put some kind of insect repellent into that.
Interesting. We have another question coming from the audience. Will green coconuts and dry coconuts provide the same level of thermal insulation? I already know the answer, but please answer it for the audience.
Yeah, well, of course, the green coconut, you would have to dry those fibers. It's a fiber that we're interested in.
Yeah.
I wouldn't recommend, and I don't think we should be using fiber with a high moisture content, because that would increase the thermal conductivity. So it is dried fiber you have to use. Yeah?
Yes, very good. Any other questions, audience? I mean, this is a very interesting area for us as a Caribbean people, seeing that we are troubled by hurricanes and storms, and there's rising temperatures, you know. I don't see 1.5 as realistic. Prime Minister Mia Motley did make mention of that is unrealistic. She sees it as much of a higher value. So this type of intervention I see as a means for us to be more sustainable and resilient. Anyone else has anything to contribute to this particular area?
Brian, I just want to ask Dr. Adeyanju,
Sure.
in terms of what would you say is the minimum amount of tons of fiber we would need to generate a minimum amount of energy on a home usage basis? Thanks.
Thank Fiaz.
In terms of, I just look at in terms of kilogram, not in terms of tonnage. I said it the other time that 1.5 kilogram we generate 1 kilowatts of energy. Okay. Thank you.
Oh, and also could I ask a question to follow on from that? In terms of feedstock, I know we talked about the coconut and those things.
Yeah.
Is there an optimal mix, if any, for feedstock to go through this process, or does it matter? I know you would have brought up your charts and shown the different values, but is there an optimal mix?
Actually, for all the feedstocks used like sawdust, the coconut husk, okay, those feedstocks, the most important thing is to be dried, okay? Dried for like 4 days and cut into small sizes like up to 3 millimeter in size before you can be able to feed it into the gasifier, okay? That is very, very important. Okay, so for better production of the hydrocarbon. Thank you.
And will this compete vastly against the petrochem industry in terms of, it follows the same process, but do you see it in terms of our energy transition and the ambition to lower our carbon footprint, that this can eventually, if it's taken up by many, to compete and to replace, if possible, the petrochem industry?
Yeah, that is possible because it's a renewable energy, and the amount of CO2 produced is very, very minimal, okay, compared to the natural, the fossil fuels, okay, for natural, that is for the energy industry, for petroleum industry. So the CO2 generated is high. But in the case of syngas, the CO2 is very, very minimal, and it can be scrubbed also easily.
What about the futures market? Is it something that is already on the futures market, Doctor?
Yeah, it's on the futures market. Mm-hmm. I told you the other time that 53% of it is being used for ammonia industry. It's being used in the ammonia industry. Okay, though some countries that have no electricity, that don't have what we call it, natural gas to generate power, those countries are already using syngas to generate power, like Cambodia, okay, like Madagascar, they're already using it. Okay, so but we can use it for ammonia, most especially in the Caribbean region, most especially in Trinidad. We can use it for ammonia production. Thank you.
And I'm not letting you go just yet, Dr. Anthony.
Okay.
Regarding the futures market, when it comes to speculators and the how that derivative is marketed compared to its cousin, which is from the fossil fuels industry, do speculators have more of a challenge speculating, or is it more of a balanced speculation when selling this commodity on the commodities market, stock exchange?
Okay, come again. No, that's not the question. Come again.
In that market, with regards to the sale of, say, this particular commodity from syngas, right?
Yeah.
Ammonia. Normally, speculators would speculate the price in the next 2-3 years and then create demand based on what they speculate the price to be. Does this also subvert that potential for speculators to maybe create an imaginary bubble that will cause the cost of ammonia to go up and move away from the volatility of fossil fuels?
I think whatever the speculation will be for the future, I think the advantage of this syngas market is in the area of renewable, okay, which is far better for when we are comparing to using natural gas, okay, which produce a lot of greenhouse gases, okay. But the case of syngas with minimal greenhouse gas, I think that one is better. The speculation for future, I think, is better to me. Thank you.
Well received. Yeah, so those are the questions that seem to have come out so far from this session. I really thank both of you for giving fantastic presentations, and in particular, the question and answer segment, which I myself have learned a lot from. I'm looking forward to that technology being taken up into the Caribbean using the coconut husk, well, the shredded coconut husk as a means of insulation. I think is a very unique and significant product that can make a difference in the construction industry. I know we're against time, so before we close, I would like to give an introduction to, and go into lunch break, I would like to give an introduction to my successor, Chair, Albada Beckham. And then the speakers would be Gas Sidus and Jaman Kundun. I yield the floor to the host, and we break for lunch.
Okay, so Brian,